Whenever you go to a collection store, you might have seen mystery packs. If you're unaware of what mystery packs are, they look like this. An opaque packaging containing the details of what possible figurine can be found inside, and sometimes the probability of each outcome is shown. A while ago, I was collecting figurines from mystery packs, and a thought crossed my mind. What is the actual probability of getting the figurine that I want? For a start, the probability does not apply when you open a pack. You are only ascertaining its identity. As such, you can liken buying a mystery pack from a pile in a shop from drawing a card from a deck. The probability occurs at selection, not at opening. However, in a shop, there are also customers who might have also bought a pack from the pile, causing the probability to change every turn. Furthermore, if you were to multiply the probability with the current pool, there will be some occasions where you do not actually get a whole number, which isn't actually possible. So therefore, it is quite unlikely that probability on the packaging indicates probability at all, although it can be a close estimate. Instead, it might represent something else, such as the proportion of the figurines in each pool that is being manufactured. Let's test out this hypothesis. Imagine that I am a manufacturer of a set of mystery packs. The mystery pack has 10 outcomes, represented by the cards with the digits 0 through 9. The frequency of each outcome is 10 for a total pool of 100. The probability of each outcome would thus be 10%. That will be written on the pack, which is true right now. I now cover the cards, shuffle them, mix them up, and split them into 3 shops. Shop A takes 50, Shop B takes 35, Shop C takes 15. I will now begin shopping by taking out the cards one by one. The table here represents the respective frequency and probabilities of each outcome. I do not actually know the values right now, it is only added post-editing. Here are the plots of probabilities against cards left for each shop. You can observe that the respective probabilities stayed rather stable at the start when there are more cards, until near the end where there are very few cards, around less than 10, do they start fluctuating. This is somewhat expected as a card makes up a smaller proportion of the total pool when the pool size is larger, as opposed to a smaller pool size, and thus would have a much smaller effect. As expected, none of the turns had all the outcomes follow the expected probability of 10%, since there are many factors which would make it very unlikely to get the desired outcome by random chance. Therefore, instead of observing if the observed probability equals the expected probability, that rarely happens, we should observe if the observed probability approximates the expected probability. In other words, does the deviation of the observed frequencies of each outcome from the expected frequencies caused by chance or not? You would first need to make null and alternative hypothesis before starting the statistical analysis. The null hypothesis assumes that the deviation of the observed and expected results arises by chance,
while the alternative hypothesis is the opposite and assumes that the deviation is not by chance. Now you can start your statistical analysis. To determine this, we use the Chi-square test. The fastest way to do this is via computation. You need the observed and expected frequencies, not probability of each outcome. Compile a range of your observed and expected values. The observed values are observed for your experimentation, while the expected values are calculated from the expected probability. Use the equal chi-square test function on Excel and input the range of observed and expected values, and you would get the p-value. If the p-value is lower than the threshold, usually 0.05, then you reject the null hypothesis and conclude that the deviation between the observed and expected frequencies is not caused by chance. If the p-value is higher than the threshold, you do not reject the null hypothesis and conclude that the observed deviation is caused by chance. As you can see, most of the time, the p-value is higher than the threshold, indicating that the deviation arises by chance and that the actual probability can be estimated by the stated expected probability. However, there will be certain errors. You've seen the whole experiment. Everything is done randomly and thus the outcomes should arise by chance. But look at shot B, 5 and 4 cards left. The p-value went below 0.05 with a value of 0.049 and 0.013 respectively. This is a type 1 error, aka false positive, where the null hypothesis is true but rejected. But from the results, 2/10 out of 100 indicates a 2% false positive error, which seems fair enough. Alternatively, you can calculate the chi-square value and compare it against the threshold chi-square value. This is useful when you do not have access to computational tools. To calculate the chi-square value of your experimental result, find the difference between the observed and expected, square it, and divide it by the expected. Find the value of the equation of each outcome and sum them up. Now, you will need to find the threshold chi-square value by referring to the chi-square table. As you can see from this table, the threshold value is determined by two factors: degree of freedom, df, and p-value. The degree of freedom is 1 less than the total number of possible outcomes. In this case, 10 minus 1 equals 9, while the p-value is your threshold p-value. After finding these two factors, you have your threshold chi-square value. Now you will need to compare the two values. As you can see here, the higher the chi-square value, the lower the p-value. Therefore, you can come to the same conclusion based on the chi-square value, except that the inequality symbols are reversed.
As with every experiment, it is important to repeat them a few times to ensure that they are statistically significant or similar. Calculating the mean value of your results will also cancel out any error margins that are caused by chance. I repeated my experiment for another 9 more times for a total of 10 attempts, and here are their probabilities, chi-square and p-values.
As you can see, most of the results are similar, showing some forms of fluctuations, particularly when the number of cards is small. Once again, most of the turns have a p-value above 0.05, except for 18 occasions of false positives in all 10 attempts, indicating an error margin of around 2%, which is similar to the first attempt. I have also obtained the mean of all the attempts and calculated the p-value. Here you can see that the results are much more stable and the p-value is close to 1, suggesting that there is little to no variation between the observed and expected values.
You can also try out this experiment yourself. You do not actually need cards or corrugated boards. I only use them for better demonstration. Instead, you will just need sheets of paper. Decide on the number of outcomes and the respective frequencies of each outcome. Tear out as many small pieces of paper equal to the total number of outcomes. Write down all the individual outcomes on each piece of paper. Crush the piece of paper to cover the identity. Shuffle them, mix them, split them into different shops or not. Open the packs from each shop one by one and note down the order that you have taken them. Once you're done with a shop, tabulate the initial frequencies of each outcome. Deduct 1 from the frequency of the selected outcome every turn. Calculate the probabilities, the chi-square, and the p-value. I have provided a Google Sheets file which calculates the stated values. It can calculate up to 20 outcomes for a total of 200 turns, though you do not need to use all of them. You can access and download it from the link in the descriptions below. So, what is the actual probability of a mystery pack? Well, you should not expect the stated probability to be the exact probability of each outcome, but you can use it as a good estimate, around 98% of the time and when the pool is large. Of course, if you want to get the figurine that you want, it might be good to actually ascertain the identity within means before you make the purchase. I might be using this video to partially brag about my collection of figurines of characters from Inside Out. As you can see, they all came from mystery packs. I bought 5 and got all 5 that I wanted. I'm just left with Anger, who came from an earlier series that's probably sold out. Did I forget anyone? I didn't, don't worry. Anyway, I will be using these figurines to build something more interesting, possibly in a future video. No guarantees yet. I wasn't able to source all the materials, so I haven't procured any of them yet. That's it, bye.